Hi, Chem students, and welcome to a lesson over electrons. Please have out your notes and something to write with.
Most, if not all of us, have seen fireworks on the 4th of July and neon signs brightening the city streets. But how is light emitted? And why do different chemicals give off different colors? To answer these questions, we must study electron movement within the electron cloud and understand the properties of light. An interesting property of light is that it can behave as either waves or particles, depending on the circumstances. This is called the wave-particle duality of light. The fact that light can act as particles and can transfer all of its energy to another particle, such as an electron, was an important fact in the development of the quantum mechanical model or modern atomic theory. In this unit, we will focus on the wave nature of light. Waves have three primary characteristics: wavelength, frequency, and speed. One wavelength is the distance between two consecutive crests or troughs and is shown in the diagram. Wavelength is represented by the Greek letter lambda. Light is composed of many waves of many different wavelengths, ranging from large waves that are kilometers in length to small waves picometers in length. When describing a wave, we usually use meters. Frequency is the number of wave cycles, successive crests or troughs, that pass a given point per unit of time. It is measured in cycles per second or hertz. The symbol for frequency is the letter F. In the diagram below, the top wave has a high frequency and the bottom wave has a low frequency. The last characteristic of light is speed. All forms of light travel at the same speed in a vacuum. This is the most accurately known constant in the world. The speed of light, which is 3 × 10⁸ meters per second, is represented by a lowercase c. Although we often think of light as the energy that enables us to see, visible light is a very small portion of what is called the electromagnetic spectrum. The electromagnetic, or EM spectrum, includes all the characteristic wavelengths of electromagnetic radiation that are emitted by an object, molecule, or atom. You've probably heard of most of these types of electromagnetic radiation. Radio waves carry the songs and information we listen to on the radio. The number of the radio station, for example 95.7, refer to the frequency of the wave. Microwaves are used to heat food and drinks. Infrared radiation is emitted by heat lamps to help keep reptiles and other animals warm and by your TV remote control. Certain types of thermal imaging devices capture infrared radiation emitted by objects so you can see them at night. Our eyes detect light in the visible light range. We see colors when certain wavelengths are reflected off of an object. If all the colors are reflected, the object appears to be white. If all the colors are absorbed, the object appears to be black. Visible light includes the colors of the rainbow, and the wavelengths range from approximately 700 nanometers to 400 nanometers. Red light, which has the longest wavelength, is just after infrared radiation. Violet light, which has the shortest wavelength in the visible range, is just before ultraviolet light. Ultraviolet light is used in tanning beds, and forensic scientists use it to detect blood and other bodily fluids at a crime scene. X-rays are used to detect broken bones. And lastly, gamma rays are emitted during nuclear reactions. To remember the order of the EM spectrum, from longest to shortest wavelength, use the saying, "Riding much in vans uses extra gas." Frequency is determined by the wavelength of a wave. Watch the wavelengths as they leave the screen. This illustrates an important property of light. The shorter the wavelength, the higher the frequency. Wavelength and frequency are inversely related, which means as one increases, the other decreases. Not all properties of light can be explained by the wave model. Max Planck, the bottom left, and Albert Einstein, the bottom right, refined our understanding of light to include its particle nature. Light can be described as a stream of particles called photons. The details of the particle nature of light will not be investigated in this class. We will only highlight the relationship between energy of light and its frequency. Light also has energy. When light acts as a particle, it can transfer all of its energy to another particle, such as an electron. Energy and frequency are directly proportional. This means as frequency increases, energy also increases. Therefore, long wavelengths, which have a low frequency, also have a low amount of energy. The low energy end of the spectrum includes radio waves, microwaves, and infrared radiation. Electromagnetic radiation with short wavelengths have high frequencies and have higher amount of energy, which is why they can cause significant damage to our skin and DNA. The high energy end of the EM spectrum includes UV light, X-rays, and gamma rays.
When light acts as a particle, it can transfer all of its energy to another particle, such as an electron. All atoms absorb and emit light when excited by electricity or heat. Elements emit light in unique, distinct patterns called emission spectra. Spectra corresponds to the movement of electrons between energy levels. Spectra are like the fingerprints that can be used to identify an element, like in a flame test, which we will be doing in the next class period. When an incoming photon is absorbed by the atom, an electron is excited to another energy level. What's more interesting than an electron being excited to a higher energy level is what happens when it drops down to its ground state. If you'll please highlight this bottom sentence. Photons of light are emitted as an electron drops back to its ground state after being excited. So we don't really see anything in the absorption process. It's the emission of light that we are able to see. So as an electron is dropping back down to its original state called its ground state, a photon of light is emitted by a specific color, and we can then identify what type of atom we're dealing with. Okay, that's all for today's video. I will see you next class period for the flame test lab when we can see some of this in action. Bye!